So now I'd like to present Jaro, our final speaker of the day. Jaro is a PhD student at Delft, and he's known as Notmare or Jaro online, in case you're recognizing him from there. And he got his start on Haskell working on the Yi text editor, which is something I always wanted to try but never have actually tried. And he's very interested in performance optimization and compiler hacking generally. Thank you.
Okay, yeah, so I'm going to be presenting my work on an extension to the compiler that has to do with higher order patterns in rewrite rules. This is also come from my interest in performance, because the rewrite rules are, of course, used to get performance. So what are rewrite rules? I expect most of you to be kind of familiar with them, but I'll repeat. You have this pragma that you can use in your Haskell source files to create user-defined optimizations rules, and you can do this by basically pattern matching on parts of core. For this presentation, I'll split it into template variables, a left-hand side and a right-hand side. And the template variables are very important here. They are the variables that will get instantiated by the rule matcher to arbitrary parts of the programs that the rules are matched on. So this rewrite rule will look for the left-hand side, fill in the variables x and y, and then replace it by the right-hand side. So one way to make that more efficient is to require that the left-hand side always starts with an identifier of a global function. So you can just, in the simplifier, just search until you hit a function and then look, do we have a rewrite rule for this function, and then apply the rest of the matching. So then it matches all the arguments to the program to get the substitution that's necessary to substitute the right-hand side in place of where the match has been found. So that's how rule rewriting works. That's a simple overview. So why would we want to extend the rule rewriting system? Well, the motivation for this proposal mainly comes from the PhD thesis from Duncan Coutts. I hope I pronounced it right. And there's one point in section 4.8.3 about fusing concat map that is problematic without or with the current rewrite rule system. So so we can't always fuse a concat map operation, but in certain situations we can. If the concat map is used in a certain form, so this form where you have concat map of some lambda which then starts immediately with a stream constructor, then we can rewrite this to this special concat map prime function, which is nicely fusible. So only there's a problem with, so you might think we can just use this rewrite rule, but there's a problem that is, it doesn't work in many common cases, such as this x times 2 plus x, because the rewrite rule matcher will try to, well, so of course the concat map matches and the lambda matches and then stream next matches, but then it gets to this last part, fx, that doesn't syntactically match with x times 2 plus x. That requires some more, some transformation before it would be possible to match. So actually, if we beta expand this x times 2 plus x to introduce this extra lambda before it, then it does get to this form where you have. So here you do have this function, which is the lambda y to y times 2 plus y, that is applied to the variable x. And so it would be able to match expressions like this. But yeah, we want to also I wanted to improve the rewrite rule matcher to be able to match the original expression. So how can we do that? I started out my approach by just thinking, well, can't we just better expand somehow when we are matching and figure out the specific cases where we do need to do this beta expansion, so where we do need to introduce this extra lambda. And so which cases are those? Well, I identified that if you have a template variable like this f here, and you apply it to this local variable called x, which is bound by the lambda, which is part of the left-hand side. So that's why it's a local variable. Then in those cases, you want to do the beta expansion. So yeah, what was my approach to contribute this to GHC was, well, start with mailing the GHC devs mailing list. I started out suggesting, well, I wrote a mail with several questions, but one of the questions was, well, in this PhD thesis, there's this rewrite rule. Wouldn't it be nice if we could extend the rewrite rule matcher to see through beta reductions? And so I think an hour later, I got a reply from Sebastian and also one from Simon, where they pointed me to useful resources. And I think the conclusion is Sebastian suggested that this looks very much like pattern unification from dependency types languages, or higher order pattern unification, which is a subset of higher order unification, which is still relatively easy to implement, but it's even just the pattern unification is considered too difficult to implement in the GHC rewrite rule matcher. But also the problem of matching a pattern against some concrete piece of code is much easier than the problem of unifying two expressions which can both contain variables. So in the case of matching, you just have one expression that contains variables and one concrete expression, while in the case of unification, you have both the thing you're matching against and the thing you so both the template and the actual program can have variables. So it seems related, but it seems to be a simpler problem. And Simon suggested looking at a paper about higher order matching, which is complicated too. There was a paper written about it by Demore and Sitampalam, who implemented this, I think also for Haskell, but it was never integrated into GHC. I don't know the whole story, but I can imagine that it was considered too complicated, and also it can give multiple possible matchings, multiple possible results, so that's not really practical in the rewrite rule engine. But there was one part of the paper which is interesting. This is a quote from the paper. To wit, a restricted pattern is a normal term where every occurrence of a free function variable is applied to a list of distinct local variables and nothing else. For such restricted patterns, much simpler and more efficient matching and unification arguments are possible. So this is like the Fermat's last theorem, I believe, which is the proof doesn't fit in this paper, but yeah, so that's suggests that, well, it might actually be a lot simpler than both of these problems to do the intersection, basically. Yeah, so what did I do? I got hacking on GHC, tried to implement it, and open a merge request. So I'll now dive into the code. So where do you even start looking for this? Well, in the rewrite rule matcher, so in the compiler directory, GHC, core, the rewrite rule matcher works on core. And then there's this module called rules.hs, which will bring you here. Yeah, so Now there's multiple ways to go about finding the actual place in this module, because this module is multiple thousands of lines long. You can start, for example, with this lookup rule and then go down the call graph to see where the actual matching happens. Or you can scroll through the file and see if you find a piece of code that looks like the right thing. I don't actually remember which approach I used. I think maybe the latter. So the actual function that we're looking for, I'll skip through to it in the interest of time, is this match function, which is eventually used by the lookup rule function. And the match function, that's really the function that takes two expressions, so this core expression template and the core expression target, and checks if they're equal. And as part of that, it takes as input a substitution, which is also returns an output. So it's kind of like using that substitution as a state. And of course, wraps it to maybe for if there is no match. And it has some environment to tell you which variables are the template variables and things like that. So the goal is to construct a substitution of the variables. Let me go back to... So we want to find, remember, we want to find a substitution of these x and y variables to, as a result of our match. So as a result of a match, we want to build this substitution. And that's this rule substitution. Okay, so there's a bunch of cases for ticks, for types, for coercions, casts, literals, variables, and applications. So this sounds like where we should be. This is actually the code I wrote for my patch, so I'll skip over it for now. The thing that I saw was this part, very short. If you have an application in the template and an application in the target, then you just match the function part of the application and you match the argument part of the application and you continue. But that's the behavior that we want to change here. Instead of just considering these two separately, we want to check, are we in the special case where we have this template variable applied to a list of local binders? And if so, do this special mechanism where we do the data expansion. So that's what I do here. If we have an application in the template and we match it to any expression, then what I do is I'll collect. So this collect arg function splits the template into a function applied to a list of arguments. Then there's some renaming required. And I'll look up if this function is actually a template variable. And then the next thing I'll do is check if the arguments are all local. And that there are no duplication. I think I didn't have this at first. At first it was a little bit more specialized to exactly what I wanted, and not as, what should you call it, as flexible as it is now. So these last two rules were not there in the beginning. So you can just start with your changes to GHC without having everything worked out. And if that is the case, then I'm building. So as I just explained, you can do this beta expansion in the target. So you could beta expand part of the target, and then the matching should work fine. But instead of doing that, it's a bit indirect to do it that way. Instead, you can directly do the beta expansion in the substitution that you're building. So you're just adding a lambda to the substitution that you're building. And that is what this make core lamps does. And for that I use a bunch of helper functions. So I wrote this initial merge request, which I opened, I think, the next day from that email. And then I got some helpful feedback from Simon and Sebastian. Things like, no, this isn't working. Well, things like, oh, you can use this function, you're using the wrong, or you're using an, there's this function to do the same thing as what you're doing in many more lines of code, and make this a bit more flexible. So you really, if you just open an MR, then you'll get some very good feedback from the main contributors, where I really, this was the first time looking at how really at the how GHC works internally. So this was very helpful for me. Yeah, so Sebastian asks, can you create test cases? Can you, I think somewhere here, yeah, can you open a ticket with an explanation of what's happening in this change? And Simon also very quickly wrote a summary explanation of what's happening. So that was very useful as a start for this new ticket, and as a start for the GHC proposal that I wrote in the end, because this started as really a change to GHC that I made, and this merge request. And then at some point, Simon suggested, well, this is actually a user-facing change, so you need to open a GHC proposal. That's somewhere here. So that was the next thing I had to start working on. Well, I had the base of an explanation of what was happening. I had my own motivation in my head. So with that, I wrote this higher order patterns in rewrite rules proposal. This is, I think I would have liked to see a bit more feedback on the proposal here. There were some enthusiastic people, but they didn't quite get what exactly was happening, and if they could really use it for themselves. One useful tip is, if you write a GHC proposal, do use the restructured markdown or the restructured text instead of the markdown option, because then you get nice table of contents, which is very useful. So I made that change. Yeah. So then just became a long process of fine-tuning each different part and waiting for some more feedback. And during that process, I also worked out the details of the merge request. So, for example, I should probably. So there's one problem when you're adding these lambdas to the substitution result. Let me see if I can explain that. That is best explained here. So what you see happening here is that I add this y variable, which is a fresh variable, and I rename all the x's in the target to this y. But instead, it's more efficient to keep these x's and rename rename the other thing, basically. So that was still a bit of a problem to figure out exactly how to do the renaming, because also the renaming substitution is a one-way map, and this actually required me going the other way. So I had to reverse the map, and actually Simon helped me a lot with implementing those parts, because I was not familiar with exactly what all the renamer environments did at the time. So I opened the MR, wrote the GHC proposal, and the GHC proposal got accepted, and then the MR got merged. Yeah, so, well, it will be part of GHC 9.8, I believe. So you can try this out on your own when that's released, hopefully pretty soon. Some future work I plan to do is actually write a useful Stream Fusion library that uses this new rewrite rule mechanism to achieve fusion of the concrete map operation. And I also encourage all of you to find other uses for this extension, because just having it for Stream Fusion seems, I mean, just achieving Stream Fusion for concrete map is a very nice thing to have, but I would like to know if there's any other interesting application that you can think of. Thank you.
What was the most time-consuming part of this process?
I think it was getting all the details worked out and writing all the GHC proposal. But that could also be because the programming itself is much more interesting. So that was like done in a day of work or 2 days of work. There's another question.
This is more of a comment, actually. I would answer your question in a different way, since I was an observer of the process. The most time-consuming bit was getting from a vague idea and some arm waving to a precise idea with a specification. And once you had that, implementing it was pretty easy. But that's a very common pattern. You have kind of, there's something nice here, but let's make it precise. And that can take a long time and seem tiresome, but it's actually very valuable.
I was thinking about this problem in the weekend, I believe, and then I sent this mail to GHC devs on Monday, and then I had like the basic implementation in 2 days after that. So the basic implementation was very quick, but indeed working out all the details and getting a good specification, that takes a lot of time. Yeah.
Thank you very much for adding on your presentation here. I think this is a reasonable idea of what you can expect as a GHC contributor these coming 4 days. So have at it. I'll see you tomorrow morning.
Thank you for allowing me to